is Marco Gonzalez, and I am an education technology consultant for Texas Instruments. There's 10 of us across that support various parts of the country. What I support is I support half of Texas. I support the state of Oklahoma as well, including and starting in 2024, I'm also going to be supporting the state of Louisiana as well with our classroom solutions as well. We encourage all of the participants to enter or to use the chat feature for questions, for comments. If there's something to add to the discussion, we encourage the attendees to use the chat feature in doing so. Right after the end of this session, when you exit the session, you are going to immediately be prompted to provide a survey. This is very, very, very important for the organizers of the T-Cubed International Conference. It provides some direction as to how we can improve future sessions going forward and so forth. We want to try to always constantly improve and provide relevant topics and really good conferences going forward. So your feedback is crucially important. And also any slide decks, any resources that is being shared throughout this session, those are going to become available through our event website after the conference is over. Just the conference organizers are going to gather everything, maybe clean up the event website, and then at that point make everything available for us. One of the things that we need to mention as well is someone from an attendee from this session will also be selected as a winner of some TI technology, and that person will make that announcement at the end of this session as well. This is a panel discussion. It's called From Those in the Know. It involves AP Calculus. Our moderator will be Tom Dick, and these are our panelists. And I'll speak a little more in detail regarding each of our panelists here. Tom is from the West Coast. He is employed at Oregon State University. He's also a national T-Cubed instructor. And he's a former chair of AP Calculus, the Development Committee. If time permits, I'll have Tom also provide a little more background in a little bit. Julie Clark is an associate professor of mathematics and statistics, computer science at Hollins University. She's also an AP Calculus chief reader and member of the AP Calculus Developmental Committee. And she's a mother of, I love these names, Pythagoras, Trigg, Tukey, Merkel, Bonferri, Bernoulli. And the last one took me a little bit to figure out. I thought it was Squirt, but it is Squirt, or is it square root?
Well, it's spelled square root, but pronounced squirt.
Oh, okay. I thought it was square root, but initially, okay. Cool. I love those names. I love those names. Stephanie is a College Board lead for AP Calculus and AP Stats, and she's taught for more than 30 years secondary and higher education students. She's also a principal investigator for Knox County Schools First to the Top grant. She's also one of our T-Cubed regional instructors. And also, finally, but not lastly, Benjamin is a senior manager at ETS for STEM assessments. He's a former College Board lead for AP Calculus and AP Stats as well. He's got a master's from Duke University, a PhD from Stanford, and something that's interesting, and hopefully Ben will talk a little more about this. He's taught calculus in Japan, well, at all levels, and he's also taught in Japan and in Finland as well. So It's great. It's an excellent group of panelists, and you'll learn more from each one as they deliver their presentations. I think the order, this is the agenda. I think the order might be a little different. I think Julie is going to speak first, followed by Benjamin, I believe, and then Stephanie will finish our sessions out. And like I mentioned, Tom is going to be moderating the chat as well as I am. And if anything else comes up, we'll be happy to entertain those questions as well. At this point, I am going to stop sharing my screen, and I'm going to pass control over to Julie.
Okay, hopefully I am sharing my screen, and hopefully you can hear me. I teach at Hollins University, and I'm the current calculus chief reader, but I'm not actually in Virginia today. I'm at the annual Chief Readers Retreat. This year it's in Charleston, South Carolina. So I'm actually gonna try to do my piece and then cut out a little earlier than I might otherwise have done, so I can get back to the retreat. So I'll know what's going to happen with the exams in 2024. I wanted to introduce you to the development committee, the committee that actually was responsible for the 2023 calculus exam. You see that our faces here at one of our meetings. Those faces include Frances Rouse, the high school co-chair. She's from Mobile, Alabama. Mark Kanowski was our higher ed co-chair from DePauw in Indiana. Eric Alquist is our College Board Advisor member, and he's from Minnesota. Mary Besiegel is from Oregon State University. Anisha Newman from Spelman in Atlanta, Georgia. Brian Shea is lucky enough to live in San Diego, California. Big Jerome White from New Orleans. And me, you're already hearing from. And then Stephanie Ogden is our College Board course lead. So she is at all of our development meetings as well. That was the 2022-23 committee. It's actually changed just starting in July. Sharon Taylor has come aboard from Georgia Southern University. She is the CRD. We love acronyms here. That stands for Chief Reader Designate, which means she'll be taking over as Chief Reader next July. This is my last year as Chief Reader. We have a new higher ed co-chair, Alex McAllister from Center College in Kentucky. And Karen Slino is a member coming onto the committee. She's from Michigan. Let's see. So you've heard already a lot about this development committee. Most of us have been or are on the development committee. So I thought you might want to know a little bit about the responsibilities of the development committee. It's our job to plan, develop, and approve each of the exams every year before they're given in May. We're supposed to participate in the reading, and you'll see many of the names of the committee members again, because we do all participate in the reading. We then consider the statistical analysis of sort of how the exam went every year as we're making up questions for the next year or years. Hopefully we're working well in advance. Then we work on reviewing, revising, and updating the course and exam descriptions, the famous CED. Everyone else advises me, tells me what to do about how to run the reading and make it go successfully and smoothly. We participate in outreach events like this one. We hopefully, let's see, since the pandemic in 2020, we have revised the meeting schedule. That we used to meet face-to-face several times a year, but now we have 1 to 2 face-to-face meetings a year, and then we have many virtual meetings throughout the year as we discuss all of these other tasks that are on our plate. So for those of you that aren't aware, the AP Calculus exams, which are given in May every year, some typical information about it. We have different, what we call forms, and they're different versions of the exam. We have a U.S. main exam, which we call the operational exam, which is given to all the students in the mainland U.S. We also have an international exam given overseas because of the difference in time zones. And then we have alternate exams, which are basically for late administrations or students that for some other reason need to take the exam at a time that is different from the bulk of the U.S. main exam takers. On each of those exams, there are two parts, two sections. The first one is multiple choice, and that always contains 45 multiple choice questions. Ben's going to say a little bit more about all of this down the road. The section that I'm going to talk mostly about today is that section 2, which contains 6 free response questions. We actually give 2 different exams in each form every year. We give an AB exam and a BC exam. Both exams share 3 common free response questions, and then they have 3 other free response questions on each of those AB and BC exams that are not in common. Of the 6 questions on each of the AB and BC exams, 2 are calculator active, and the remaining 4 are questions that they are supposed to answer without access to a calculator. So how did the reading go in 2023? This was our second year of having what we're calling a hybrid reading. In 2020, of course, we had to turn on a dime and both administer and score the exam from home. In 2021, we continued with the scoring at home, but in 2022, we had our first hybrid reading where we had some people come to Kansas City to score in person and then some to read from at home. We repeated that this year. We had a lot of leadership personnel helping us out. I was there. We had 3 ACRs, assistant chief readers, Steve Kokoska, Alex McAllister, and Sharon Taylor. We had 8 ELs with us. EL is short for exam leader. Verge Cornelius, Stephen Davis, Tom Dick, Mark Corrali, Christy Meyer, Tom Pulaski, Francis Rouse, and Karen Slino. Some of those names you've already seen before. We had 36 QLs. I won't list all 36 of them, although I probably could. And they were each in charge of one of the questions on one of the forms to set standards for how we would grade them and provide samples and scoring guidelines so that we graded everything consistently. We had 63 what we called early table leaders. They were table leaders. They served as table leaders once the reading began, but they also came to the pre-reading. So they came to Kansas City early to help out the question leaders in preparing the scoring guidelines for those questions. Once the reading started, we had another 79 table leaders. 21 of those were in person in Kansas City and 58 were reading from at home. I just have to say thank you again to those table leaders who really do the bulk of the work for us at the reading. They're the one role we just couldn't do without. We had 1,170 total readers. 385 of them came to Kansas City. Another 785 read from at home. That makes, oh, right, we had one more. We had a CRD. That's a little misleading. Mike Boardman served as a CRD this year, but he wasn't going to take over for me in 2023. He's actually becoming the new chief reader for pre-calculus, a subject we're adding in 2024. Altogether, that made a total of 1,361 of us that were scoring papers this year. Thought you might like a picture. These were all the folks that came to the reading in advance for the pre-reading. So that's all our leadership team. Whoops. We ended up scoring about 410,000, 410 to 411,000 total exams, which if you multiply by 6 means that we were just under 2.5 million questions scored. Fortunately, I did not have to score very many of those. I didn't have to score any in Kansas City. Yay. In case you are not already on the list to be an AP reader, I wanted to point out some real advantages to it, some reasons you might consider it. Everyone who does it will tell you that it's a great experience. I know it sounds terrible, but it really is a tremendously fun experience. And in addition, it can lead to some really positive changes in your classroom. You get to interact with other teachers and educators who have some really great ideas. You learn how to score consistently and fairly according to the rubrics, so you get some great training on how to score these. You get exposure to student responses well beyond just your classroom, so you get to see across the board student responses, which is invaluable. And of course, you get paid. And if you come to Kansas City, you also get fed more than any human being can eat in a 7-day grading period. And if you're interested, you can also earn continuing ed credits. So again, if you're not already a reader for us, you might go visit thecollegeboard.org /AP reading and sign up. We'd love to have you. So how many exams did we score and how did they split out this year? So I have a couple of bar charts here. On the left, you can see the exam volumes for the AB exams. And actually these charts record from 2019 through 2023. Of course, 2022 is a bar you really should ignore, but you'll notice that in 2019 on the AB exams, we were starting to lose a little bit. We didn't have quite as many exams, AB exams taken in 2019 as we had had in 2018. We were seeing a slow decline in AP calculus exams then. We saw a pretty marked decline, a drop of 11.4% in the AB exams in 2020, but of course that was the pandemic year. In 2021, we saw another small decline, another 5.6%. But then we saw a rise, quite a large rise of 6.6% in 2022, and another small rise in 2023. We actually suspect that in 2022, part of that rise was several students who had taken BC classes, but elected to take the AB exam because they didn't feel quite prepared enough to want to take the BC exam. And that suspicion is sort of supported when you look at the BC volumes. BC volume in 2019 was about the same as it was in 2018. We had a drop off in 2020, but notice it wasn't quite as steep a drop off as we had in the AB exams. We had not nearly as a big a drop off in 2021, only about a 2.6% drop. We did see a drop in 2022, unlike what we had with the AB exams, but we think that drop in 2022 was due to BC students who had taken the BC course deciding to take the AB exam. Notice the growth in 2023, BC exam rates went up 13%, which is just terrific. In fact, that's a real boom here. This is basically back up to the pre-pandemic level of BC students, which is wonderful. Here is score distributions for the AB exams. About 58% of the students who took the AB exam this year scored a 3 or higher, which is most colleges give credit for a 3, 4, or 5. So we consider a 3 or higher to be passing grade. So this was terrific. No real problems here, and this is almost back to the 2019 level of scoring on the scoring of 3s or higher on the exam. So here's another bar chart showing you what happened in 2021, 22, and 23. 58.4 scored a 3 or higher in 2021. We had a dip in 2020, but we saw some recovery in 2021 and 2022, and we're right back to that level now in 2023. So no real complaints there. We think pandemic effects are starting to fade. In the BC exam, we're thrilled to say that 78.3% of the students scored a 3 or higher, which is terrific. Comparing to previous years, in 2019, 81% of the students scored a 3 or higher, which is a little bit higher than we saw this year, but not much. In 2022, remember, a lot of those BC students we think were taking the AB exam. So we saw a little bit of an increase in the percentage of 3 and higher in 2022 over 2021, but that was in spite of fewer students taking the exam. And this year we see that rise to 78.3% in spite of the fact that we brought an additional 13% of students taking the BC exam. So, reminder, there are 3 questions that are common to both the AB and the BC exams, and here are combined scores, individual AB and BC scores and combined scores for those 3 common questions. The first one, AB BC 1, was a question about modeling rates. They had to provide a Riemann sum. They had to talk about the mean value theorem, and a reminder that questions 1 and 2 both require a calculator. Notice that the AB mean was 3.81, and all of our questions have 9 possible points. So that was about a 42.3% average score on the exam, which is terrific, especially for the first question on the exam. BC mean was even higher, nearly 60%. The combined mean was a 47.5, and that's right where we would like it to be. That helps us distinguish across all 9 points so that we can, distinguish weak students from mediocre students to medium students to good students to excellent students. Question AB3 BC3 involved a differential equation. They had to draw a slope curve, if I'm not mistaken, and solve a differential equation, all of this without a calculator. This is very hard for some students, particularly the AB students. This differential equations was not always part of the AB curriculum. So some classes, AB classes, don't actually get to this topic. So the fact that they can tackle it at all is wonderful. You'll notice that means on this question were down noticeably from AB BC 1, but still performance wasn't terrible. AB 4 BC 4 was our graphical analysis question. So we give them a graph and ask all kinds of things about the graph. In addition to that, in the middle of this graphical analysis, they had to use L'Hopital's rule. This was, no question about it, the most difficult question on the exam, both AB and BC, for all of the students. It was the lowest scoring question, but notice that the BC still had an average score of about 45.2% of the possible points. So still looking pretty good. On the remaining AB questions, AB2, which was a reminder, another calculator active question dealing with acceleration and distance traveled and total distance traveled. The average was a 4.63, which is 51.5% of the total points. Probably the highest mean I've seen on an AB question in several years. That was terrific. Notice, however, that AB5, which involved drawing values from a table and using the fundamental theorem of calculus, had a mean of 49.8 of the total possible points. So both of those scored really high on the AB exam. We were really pleased with that. AB6, a different situation. This was an implicit differentiation problem, also involved some related rates. It was the last question on the exam, and so the averages on question AB6 are usually lower than on other questions. They tend to run out of time, they've run out of steam, and implicit differentiation is clearly not one of the students' favorite topics. It might be mine, but it is definitely not one of their favorite topics. The remaining 3 BC questions. BC2 was a parametric political motion question. It did involve a calculator, and notice that they earned 58.4% of those 9 possible points on average. Terrific. BC5, which was an area volume, involved both an improper integral and the need to integrate by parts. The average on this was again terrific, 52.8% of those 9 points. And question BC6 is usually, almost always a series question of some sort. This year they had to deal with Taylor polynomials and the Lagrange error bound. Question 6 never allows a calculator. Their score on this was 4.25 on average out of those 9 points, which is terrific. We don't usually see scores that high on the series question. Remember, this is the 6th question for the BC students, so they've often run out of steam there. And Taylor series, Taylor polynomials is another topic that often is not completely covered by teachers who run out of time at the end of the school year. So if you want to look a little more closely at this, here are bar graphs of the results for all 6 AB questions. I realize these are a little small, so I'm going to show a couple of different views of this, but the dotted lines show you what the mean score was going from 0 to 9. One of the things you'll notice about all of these is that there is unfortunately a very tall bar at the 0 or no response end of the scale. And unfortunately, we still have a problem with far too many students earning 0 points or leaving the question entirely blank. That's an NR or no response. I think those 0 scores are a little misleading because we give them a 0 even if they didn't write anything mathematical on the page. As long as they wrote something on the page, they score a 0. And often there are responses that write nothing relevant, or the only thing mathematical on the page is the student recopying the problem. So I think that those zeros imply that students weren't able to get into the problem, but I think the students who weren't able to get in weren't trying to get in. You'll notice the nice semi-bell-shaped curve here on ABBC1. We were really pleased with performance and with how it discriminated and spread out those scores across all 9 possible points. You'll notice AB6 was our low-scoring question. We just didn't see much. Many of the scores above a 2, and we saw way too many zeros or no responses there. You can see that AB4 was one of the most difficult questions. They found it really difficult to score above the 6 points. Wasn't that hard, but scoring those last 3 points was very, very difficult for them. Here's sort of a better summary of those scores, a reminder of what the average was on each of those 6 questions. The standard deviation, which notice was very similar across the questions. This is just for the operational exams, so the exams taken in the mainland US. I've also shown you here the percentage of those scores that were 9s and that were 0s. This really stands out on AB2, which remember was the acceleration total distance traveled question. I have in previous years never seen it in the 10s. I've never seen it above single-digit percentage in the 9s before. So notice that both AB2 and AB5 had percent 9s above 10%, which is fantastic. AB3 and AB4 not so great, but I was actually very pleased with the percentage of 9s. Here is another graph which lets us sort of look at difficulty of question and how well we're spreading out the scores. Ideally, we're going to see that these are fairly even jumps as we go from 1, 2, 3, 4, and up to 9. And ideally, we would have them up here at 100% but long before they got to 9. We'd like for students, these, by the way, are the percentage of students scoring 3, 4, 5, and so on and so forth, or below that problem. So for example, AB2 was an easy question. We liked that because by the time we got to 9, 80% of the students were scoring 9 or below. That's terrific. Questions AB3 and AB4 here at the top were definitely harder questions. Here are the BC results. You'll notice that we see a lot more of the higher end scores on the BC problems, and we don't see one standing out as being particularly harder than the rest. The averages are definitely higher on these. I'm seeing in the chat that someone asked how many perfect scores we had this year, and the answer is I don't remember. I know we didn't have any perfect scores on the multiple choice AB, but we did have perfect scores on the free response, both AB and BC. but I don't remember how many there were. And there were students on the BC exam who scored all of the multiple choice correct and all 9 points on all 6 BC questions. It wasn't very many, but there were a couple. So, but I don't remember how many. So here's that more information. Look at the percentage of 9s we had on the BC questions. Almost 20% of BC2, and again BC5 more than 10%, and none less than 1%, which is fantastic. All of these percentage 9s are better than what I saw in 2021 or 2022. Percentage of 0s actually is not as high as you might otherwise think, and certainly not as high as they were for the AB scores. So I'm not unhappy about that either. Number of students taking the mainland BC exam, 57,000. So looking pretty good. Here's the same chart for looking at these, and you can see that once again, BC1 has a nice concave up curve until you get to about a score of 6, and then it becomes concave down, indicating that they didn't have much trouble scoring the first 6 points. They had to work a little harder to get those last 3 points, but they were doable. You can see that BC2 was the easiest question among the BC questions. I don't really have time to go through all 9 questions, but I wanted to talk just a little bit about the calculator active questions on both exams this year. Since this is a TI conference, I thought you might be interested in how students dealt with the questions where they could use their calculator. So I'm just going to zip you through. Question AB2 was a calculator active question. This was, of course, just for the AB students. Stephen was swimming in a 50-meter long pool. He was swimming for 90 seconds. We gave the velocity of Stephen swimming, and T is measured in seconds. Velocity is measured in meters per second. Then we asked the students to find all times in the interval from 0 to 90 seconds when he changes direction, to give a reason for your answer. It turned out they could obviously use a calculator for this, but they didn't need to because it was fairly easy to look at this and see when the velocity was 0. They probably did need to use their calculator to give us the reason for their answer, because they needed to do more than just find that the velocity was 0 at time t is 56. They needed to know that the velocity changed signs there. Find his acceleration at time t is 60 seconds, show the setup, indicate units of measure, and then is Stephen speeding up or slowing down at that time, and give a reason for your answer. Find the distance between his position at time t is 20 seconds and his position at time t is 80 seconds, show the setup, and then find the total distance he swims from when he starts to the end of our time interval, 90 seconds, show the setup for your calculations. We're moving toward reminding students to show us the setup every time they have a calculator active problem, because we want to give them full credit. And just giving us an answer without showing how they use their calculator or what they entered into their calculator will not get full credit. So let's see. What sort of problems did we see in student responses here? We didn't see much in the way of calculator errors on the AB question, which was really good news. We did see in part A that they found that his velocity was 0 at time 56, but then they didn't go on to say that that was when he changes direction because the velocity changes sign. They just said he changed directions there because his velocity was 0. So that wasn't a calculator issue, but it was a problem with them explaining how they knew that's when the velocity changed signs. In part B, remember, we asked for the acceleration at time t is 60, and was he speeding up or slowing down then? The biggest problem we had here was that students correctly evaluated the derivative of the velocity at time t is 60, but they didn't tell us that that's what they were doing with their calculator. They just reported the acceleration. So crucial that students remember to show us the setup. And when they're, if they're using their calculator to find a derivative, they need to tell us that they found the derivative. They can't just label it as acceleration. The other error they made in Part B was evaluating the sign of that acceleration and deciding that that determined whether he was speeding up or slowing down. They didn't include information about the sign of the velocity. And of course, they need both the acceleration and velocity to determine whether he's speeding up or slowing down. Parts C and D basically asked for integrals. One was net distance and the other was total distance traveled. And we had a lot of students who interchanged those two. They couldn't remember which one was which, and so they wrote the wrong integral for Part C or Part D. Some students wrote the same integral for Part C and D. They just changed the limits. Changing the limits was good, but they shouldn't have been integrating the same integrand in both cases. I wanted to talk about BC2 next. It was a similar acceleration distance displacement, but it was in terms of parametric particle motion this time. So we gave them the function for the y coordinate was 2 sine of t, and we told them what the derivative of the x coordinate of the particle's position was, and we told them where the particle was at time t equals 0. In Part A, we wanted the acceleration vector at time t is 1, show the setup. Part B, find the first time at which the speed of the particle is 1.5, show the work. Part C, find the slope of the line tangent to the path of the particle at time t is 1, and then find the x-coordinate of the position of the particle at time t is 1. And finally, find the total distance traveled by the particle over that time interval, show the setup. Again, this was calculator active, so we were expecting a lot of calculator work, which is why we asked for so much of the setups here. In Part A, where they were asked for the acceleration vector, we did have some students, enough to notice, who reported the velocity vector instead of the acceleration vector. If you look at the functions that we gave them here, the position vector of the y-coordinate was a nice function, 2 sine of t, and they didn't necessarily need to use their calculator to find the derivative here, and they didn't need to use their calculator to evaluate at time t is 1, because we would accept an answer of 2 sine of 1 if they were evaluating at 1, for example. So they didn't necessarily need their calculator. But if they didn't use their calculator to take derivatives, then they often got into trouble and made errors in differentiating by hand, which led to subsequent errors. For example, if they differentiated by hand and made an error in finding the velocity, then they often had an error in finding the acceleration as well. They did, in Part B, where they were asked to know at what time was the particle speed equal to 1.5, we did see calculator issues here with them not knowing how to solve that equation. Instead of finding the time that reached a speed of 1.5, they tried using t is 1.5 in an equation for the speed of the particle. They did know what the expression for speed was, but they didn't know how to solve. Other problems they had here were that when they set up the correct equation to find the speed at time t is when the particle speed was 1.5, instead of using the solve function on their TI calculators, and solve function is there, they often tried to use their trace function instead, and that did not give them a value that was correct to 3 digits after the decimal, and so they lost a point for that. So teachers, if you're not actively teaching them to use the solve function instead of the trace function, please do so, because it can make a difference. And it did in this part. On Part C, when they needed that particle's x-coordinate at time t is 1, the real biggest issue we had here was in communication. They like to leave off differentials when they're writing integrals for us. And in this case, it was problematic if they decided to add on that initial condition after the integral and they didn't have a differential, then we didn't know if they meant the integral of e to the cosine t plus 1, or if they meant the integral of e to the cosine t evaluated from 0 to 1 plus the number 1. So that could be costly for them. We should be working harder at making sure students understand the need for a differential and include it every time they write an integral. In Part D, with the total distance traveled, some did not know how to write the total distance for a parametric, a particle with parametric motion. So we got answers like this for the setup. But most amazingly in this part was that we got the correct setup here. This was beautiful and what we were expecting, but this is not the right value. This is the value you get if you integrate this function without the square root, which was somewhat surprising because the students clearly knew they needed the square root, but then they didn't actually use the square root when they were evaluating on the calculator. So I think I had better quit. The slides will show you a couple of things about ABBC1, which was the other calculator active problem, but I'm going to shut up now and move on so that Ben has time to talk.
Hello, everyone. Let me see if I can share correctly here. Can you all see my screen okay? Excellent. So thank you, Julie. My name is Ben Hedrick. I am the Senior Manager for STEM Assessments at ETS. What that means is I still have my hands in the workings for AP Calculus, AP Statistics, and the exam development, but I currently oversee the STEM team at ETS, which is the test developers for, oh goodness, Calculus AB, Calculus BC, Statistics, Biology, Chemistry, Computer Science A, Computer Science Principles, Environmental Science, Physics 1, Physics 2, Physics E&M, and Physics Mechanics. So about 11 different groups in total. You may hear me talking a little quickly right now. I want to make sure that I leave plenty of time for Stephanie, who is not only more important than I am, but also more interesting than I am. So what I'm going to be doing is talking about a bit of the nuts and bolts. I want to talk a little bit about some of the exam features that may be helpful to reinforce or go over again. And I'm going to talk a little bit about some of the resources that will help you prepare your students and give you some important information to prepare your students for the exams. So the first thing that I want to talk about is the course and exam description. Julie mentioned this before. We call it the CED. Sometimes we call it the new CED. It looks like this. You may recall the gray book. You may recall a version that was orange with a picture of the Kauffman Center in Kansas City. Those are older course and exam descriptions. So this is the document that you absolutely want to be using to prepare for your course. It is available on AP Central. So if you do not have a copy of this downloaded or printed or both, I strongly suggest you do that today. It is the core document for everything that you need to know. As I said, we call this the new CED. It's been effective since the 2019-2020 year. It updates some of the things in that orange curriculum framework that makes things clearer for students and teachers so that we can help you better prepare your students. The CED organizes calculus into units. Each unit is broken into topics. This was one of the biggest changes from the previous one, and it allowed College Board to produce so many more targeted resources that you can use and probably have used on a regular basis to prepare your students for the exam. The 8 units for AB, I'm not going to read through them, look like this. They go from exactly where you'd expect, starting with limits and continuity, working all the way up to Unit 8 with applications of integration. Calculus BC adds 2 more units with parametric equations, polar and vector valued functions, and Unit 10 on infinite sequences and series. That makes up the sum total of the topics and units that are in Calculus AB and Calculus BC. One of the things that deserves more focus, I think, sometimes than we give it, is the mathematical practices. I think as teachers, we know that these things are important, but they do have an effect on what your students are going to be seeing on the exam in both profound and subtle ways. If you have not taken the time to look through the practices and really get a sense of how they work, that is another thing that I would recommend as a take-home for as soon as possible. The practices are implementing mathematical processes, connecting representations, justifications, and practice 4, which is only assessed in the free response questions, which is communication and notation. As Julie mentioned, some of the things are more subtle. If you're looking at leaving off differentials, that can have an effect for a student on the exam. But we do test things like, what does notation look like? How well do you communicate? Think of something like a justify your answer. Anytime that appears in the free response section, that's practice 4. That's communication. And there are points that your students can earn for good communication, but those are points that your students will not earn if they have not been trained properly in how to communicate their answers. So even though this isn't in the nuts and bolts in terms of content, those communication, those notation points are very much deserving of classroom time to make sure your students are prepared to talk mathematically on the AP exam. Now, in the other part of the CED, some things that you may be more familiar with, this is an understanding by design in the course and exam description based on big ideas, which for calculus we've defined as change, limits, and analysis of functions. And those are further broken down into enduring understanding, learning objectives, and essential knowledge, sort of going by grain size. Big ideas are the largest, essential knowledge is the smallest. Learning objectives, I think, are one of the nuts and bolts for what we're looking at on the exam. Every multiple choice question is tied to a single learning objective. So if you want to know what it is your students are going to be assessed on, those learning objectives form the core of how those questions are created and how your students are assessed. The essential knowledge provides the information that students need to be able to meet that learning objective, but the learning objective is the target for assessment for the multiple choice questions, and it's also the target of assessment for each point of each free response question. As Julie also mentioned, I'll quickly talk about the format of the exam. It is in two parts. The first part is multiple choice, 30 questions in 60 minutes with no calculator, and then 15 questions in 45 minutes with a calculator. Following that is the free response section. You begin with 2 questions, 30 minutes. There is no separate time for each question. It's a block of time for 30 minutes where students are allowed to use their graphing calculators. After those 30 minutes are up, students are allowed to open up the section for the free response for the non-calculator questions. They are required to put their calculators away, but they are welcome to go back to the calculator active questions, even though we have passed what some students think of as the calculator section time. If you think about what Julie was presenting with some of those things with differentials, that's where it's important is if a student gives a numerical answer, we have a better sense of where that differential is. If a student stops, leaves that information there, but let's imagine from Julie's example, they correctly put in the differential, they will earn the vast majority of points for that free response question, even though they have not calculated the numeric answer. So this is one of the things that's important to know is the technology is essential for the course. It is part of it, but not everything you need. So make sure you're having your students learn how to use those calculators appropriately, know what functions are assessed on the AP exam, but also make sure your students are doing the setup to get all those points that they're able to earn. In terms of what you're going to be seeing in the questions themselves, from multiple choice questions to free response questions, we have a very elaborate scheme we call the form and assembly specifications that tell us precisely how the exam must be written. So we do have a variety of function types: algebraic, exponential, logarithmic, trigonometric, and general. We might say a function f and not give any explicit form for it. We also do analytical representations, graphical, tabular, and verbal representations of functions in the exam. Those 8 units for AB, those 10 units for BC, we have content coming from all across them. They are all represented. And some of the tasks are more procedural in nature, and some of them are more conceptual in nature. We also include questions in a real-world context, and include questions or parts of questions that do require use of that graphing calculator. Technology is valued in our course, and therefore it is assessed in our course. If you are interested, this is a question we get all the time. This is not hidden information. If you want to know how this exam is put together in terms of what percentage of questions come from which units, that is published in the course and exam description, and this is a screenshot of it here. So I'm not going to go through the numbers, but if that is not something that you were aware of, please check out your course and exam description. There is a ton of useful information in there. Those descriptions also go for how the practices are assessed, both the practices for multiple choice, which again are only 1, 2, and 3, and the practices for the free response questions, which are practices 1, 2, 3, and 4. All of this is laid out in the course and exam description. Coming close to the end here, so I can turn over to Stephanie, we do have free response instructions. They emphasize good mathematical communication and writing. They look like this. And honestly, we have always been concerned, we being the broad calculus community, the students don't read the directions. And I think because of that, sometimes they might set themselves up not for as much success as they would have been. If you have an opportunity, please make going over these exam instructions part of your course, something that you do, and take a couple of minutes during class time. One of the wonderful things that Stephanie led the way on for 2023 was inclusion in the calculator section of the instructions show the setup for your calculations. That instruction has always been here. It's been there for years and years and years, but we continue to see students who are not showing the setup for their calculations. And Stephanie said, let's make it even more explicit. If we have to be redundant, let's do it. It's better for students. It lets them know the calculus that we want to see, the calculus that we need to see. So please take a moment, read those instructions. They go over everything from, explaining justification to saying what notation is correct in terms of calculator versus non-calculator. It talks about what a function f is. It's well worth the time to read. And just to finish up, last bit of important information, when are those exams coming up in 2024? The main administration is going to be paper in schools, so not digital exams like we did in 2020 or 2021. It's going to be on Monday, May 13th. And the second administration, the makeup, is going to be on Friday, May 24th. And I'm going to finish there so that Stephanie can take over. If I can figure out what the magic button is.
Am I sharing?
Yes.
Yep,
Okay.
perfect.
Thank you, Ben. I'm going to skip the first few slides, which is why I'm not yet putting this into presenter view, but I just wanted to let you know what I'm skipping. What makes a great exam? What makes a great question? How'd we do on some of these questions? And I'm going to skip down to the slide where we think about some advice for how to make that work for your students. And the long and short of those slides is every point has a purpose and every question has a purpose. And some points are designed to be entry points. We do those on purpose to tell the difference between students who maybe are ultimately going to earn a 1 or a 2 on the exam. We want to use every single point, and entry points are for that. This is the question Julie talked about, Stephen swimming. And one of the things is try every part. If you go to part B, a lot of times students, maybe think all the entry points are early on. Part B has a really easy entry point. We have a velocity function, which is trigonometric. And it says, find Stephen's acceleration, show the setup for your calculation, and indicate units of measure. Students need to be trained to read that carefully. And then the last tip I have is practice so that you earn every point you thought you earned. A lot of students thought they earned a perfect score, but they left some points laying around. So for example, in this one, a student who did not write v prime of 60 equals negative 0.036. That student is not going to earn the first point because they didn't show the setup. It's something that they did in their calculator and didn't tell us about. Also, the question asked them to indicate units of measure, and that was the second point. Speaking of practice, that's really what I want to spend most of my time on here, and I only have 4 minutes. It's really an important new resource that we're doing, and I'm going to show you how to find it and describe it to you briefly and show you some examples. That's a lot in the amount of time I have. If you go to AP Classroom, you're going to find on the left-hand side, when you first go in, resources and assignments, all resources. And then this is the all resources page where you'll find progress checks, quizzes, practice exams, videos, and student practice. If you go to student practice, it describes what it is. Each unit has 3 problems, one at each of 3 difficulty levels, a level 1, level 2, level 3. These are designed to help those students that we sort of lose in September or November along the way because they can't quite enter the content. And so we've designed really scaffolded questions with lots of tips and so forth to help those students and give them the opportunity to actually engage all year and be ready at the end of the year. So this is a commentary on AB3, BC3, which was one of the more difficult questions. You can see that in terms of the AB3 students, we didn't do a very good job of using all the points. We didn't use the high points. The BC3 pool did pretty well in terms of that. Every single point level has representatives, but nonetheless, this is a way that you can use student practice to help prepare for even the more difficult questions. Part A, a slope field. And if you look at the differential equation, it's 1/4 40 minus m. And if you're an experienced teacher, you know that that's why this question was so hard. If you don't see it yet, you will soon. But that 40 minus n requires some substitution type thinking and in logarithms in the game, so it's kind of hard. But the slope field, the reason that students didn't earn this point, because look at the number of zeros, it's a fairly high number. They should have earned this point, tended to be either because they didn't pass through the point at right here, or they interacted with the asymptote inappropriately. They maybe crossed it in some way, or they didn't span the whole width. And so a level 1 question for that topic starts out with a defined differential equation. And I want to go through it, even though it's not a similar part. I'm going to do it as fast as I can. But you can see what level 1's flavor is. First of all, there are step-by-step tips. There are 4 tips here. And to get a tip, the student has to write something. What is this overall question asking you to find? What kind of response are you expected to provide? So I put in slopes at 12 points. I was being an entry student. And then once I do that, it tells me part A is asking you to find the value of the differential equation at each of the marked points on the given axes. You're expected to sketch a segment through each point with a slope that matches, and so on. If they go through 4 tips like that, by the time they get to the point where they're checking the answer, they know how to do this question. Also, the video explanation is available for all levels. Level 2, part A, is more similar to the question on the exam. A portion of the slope field for this differential, it's a fun little differential equation. And I wanted to show you what the tip was for this level 2 question. Part A is asking you to sketch the solution to the differential equation that passes through the point pi 3. Your response will be a smooth curve that goes from edge to edge of the provided graph in the XY plane. By the time they get through 4 tips, they're going to know how to do this question. And finally, the big baddie, I suppose, the separable differential equation, the one that we have, they have to integrate 1/40 minus m, and that was very difficult for students. The one that we have for level 3 is actually rather similar to that, only the students had to write their own differential equation. In the interest of time, I'm going to show you what it looks like. dB dt equals 0.135 times 275 minus b. That's very similar to the one in 2023 exam. They have to separate, anti-differentiate, and so on. And all the steps are provided, the explanations to the right. And so you can see that a student who worked through this particular question would have been well prepared for a very difficult question. And with that, I think I tried to finish at 4:15. I think I succeeded. We'd like to thank you for coming, and thank you for inviting us, Tom and Marco.
Stephanie, thank you so much. Thank you, Ben. Thank you, Julie, for your presentations. Let me quickly share my last 2 slides. Here, okay. So, I mentioned at the beginning that we were going to select a lucky attendee to receive a TI graphing calculator, and the winner for the calculator in this session is going to be Miss Gloria Schlatter. So please, Miss Gloria, if you could send us your email address through the chat. We are going to get in contact with you and figure out how to send that to you. So Gloria, if you could send us your email address through the chat. Thank you all very much. Thank you all for attending. We hope that you found all this information very useful. Thank you once again to our panelists, Stephanie, Ben, and Julie. Tom, thank you all very much as well. And you all have a great rest of the afternoon, great weekend as well. And we'll hopefully see you guys soon. Thank you so much.
Thank you.
Thanks, everybody.
Bye-bye. Maybe it's anybody ever stay after to ask any questions?
I am monitoring the chat. And no questions, just a comment. Gloria loved the presentation as well.
Well, of course she did. She did. She won the calculator.
Yes,
Good for her. I'm glad she won it.
yes, yes, yes. Cool. So,
Stephanie and Ben, thanks again so much for participating in this. That's always great to hear from those in the know.
I don't know if I still didn't hear it right, but I think it's Jen who helped me get in, and I want to thank her. I'll find her phone number and text her or something. But if she's still listening, I wanted to thank her for her help.
she's the one that got you the link to join?
Yes, but it didn't behave as we expected, but miraculously I was in, and I don't know, something happened. She had me join as a participant, but I actually joined as a panelist. I don't know how that happened exactly.
Oh.
So, and I was live apparently. I'm sorry. I hope that my mic wasn't, I hope I figured it out soon enough to not be too disruptive.
No, I don't think any of that came through. So no,
Excellent.
You were
Yeah.
fine.
I was
you
sitting
were
there with my
fine.
camera on and my phone. I know that. Okay, I muted myself as soon as I could. So,
Ben,
all right.
welcome back from your travels.
Thank you. Thank you. Thanks for having us here too.
Japan, is that right? Is that where you were most recently?
Yep, it's been 10 years since I was back, so my atrocious